My name is Mahesh Prakriya. I'm the program manager who's been responsible for performance in the .NET Framework team for the past year and a half. And I'm actually moving on to look at some of the other things, but actually I have a tremendous interest in perf, and I'm interested in hearing from you on any performance issues or questions that you may have. So please feel free to email me if you have any questions, issues, or anything like that. I'm going to point some resources out as well towards the end of this talk. So let's look at what we're going to talk about. There's a lot we're going to talk about in this here, and then there's some that I'm just not able to get to. For example, we'll look at what does the perf of ASP.NET and WinForms apps look like on top of this platform. And then we're going to look at some aspects of these technologies which you can take advantage of. For example, some tips and tricks in the context of ASP.NET and client-side apps. And after that, we're going to drill into CLR to a good amount. For example, we'll talk about the garbage collector and some tools you can use to introspect into the GC to see what is on the GC heap, so you know what allocations are happening from your application. We'll talk about the just-in-time compiler and some of the optimizations that it does. We'll talk about managed, unmanaged transitions and what they mean, what kind of costs you're paying, and things of that nature. What I'm not going to get to in this talk is things, detailed remoting or anything else here. However, the set of white papers I pointed out to you on the performance resource kit that you got as part of the 6 CD pack or however many CD pack does have white papers that talk about much more detailed tips and tricks in the context of ADO.NET, in the context of CLR, that talk about, I'm not going to get into finalization and disposal aspects in this talk, but that paper gets into a lot of that. So feel free to check that out as well. We'll talk about some performance counters and profilers as well towards the end of this talk. And then we'll have the Q&A. So let's talk about the .NET Framework. The .NET Framework consists of, I'm sure all of you have seen this diagram, but I like to bring this up mostly because I'm actually going to talk about the entire stack and look at the performance of the stack in the context of some ASP.NET applications and in the context of WinForms apps as well. So I'm going to have both good news and bad news, well, somewhat of a bad news for you. I mean, it's not just good news with this product. So there's some trade-offs that you have with respect to the performance tuning that you can do. And we'll talk a ton about CLR because I'm from the CLR team, and then we'll touch briefly on data and XML. I just won't have time to get to that on it. So think of CLR in this world as the kernel of an operating system, and everything about that as sort of class libraries exposing functionality, various different functionalities, starting with the base classes, primitive types, and others. So let's talk about, for the next few minutes, we'll talk about web apps. Let's talk about some of the work we've been doing. For example, we have MSN.com ported to managed code, and it's going to go live next week. And if you think about the scale of MSN.com, it's really sometimes number 2, sometimes number 3 on the net. It actually ties with Yahoo many, many times, depending on what the news is and things of that nature. It gets somewhere between 50 to 100 million requests per day. And we're running those types of sites on top of our technologies with our beta bits, with our beta 2 bits actually. So they're going live with our beta 2 bits pretty soon. And similarly, not just internally, we have some external customers such as Dell and US West, and you heard about the Verizon one in the keynotes yesterday, and on and on and on and on. We have several customers writing and deploying apps that perform really well on top of this platform. And then, of course, we care about benchmarks, and there's several samples and benchmarks that we track. For example, the FM stocks, the Wamish, iBuySpy, and others are things that we've been tracking internally, comparing to how do they do with respect to our Visual Studio 6 related technologies such as ASP and other aspects. And we also care about benchmarks So we're going to look at Nile and see how it does, and we'll look at it both with respect to our technologies and also with respect to Java server pages as well. And so let's talk about Nile. Yesterday, Paul Flessner showed a slide in the keynote that talked about the performance aspects of Nile and how do we do. He didn't have time to get into the details of Nile, but let's talk about that. Nile is an e-commerce app that is just a front end to a large back-end database that allows you to buy books, that allows you to search for different books by authors and things of that nature. All the standard stuff that you would do in any e-commerce app. It's historically been used by DocuLabs and PCD to measure the performance of app servers. For example, it is used to measure the performance of things like WebSphere and others as well. And it's a pretty good chunk of code. It's not a huge amount of code, but it's a pretty good chunk of code. And we use session state and things of that nature that you would use in any real application in Nile. And this particular benchmark tests a mix of ad hoc searches, new customer creation, and end-to-end shopping cart transactions on Nile. And we've used Benchmark Factory to measure the performance of Nile, mostly because PCD does the same thing. They use Benchmark Factory to measure that. And you can use any tool to measure the performance of these applications. For example, you can use our Homer or Act or any other tool as well. So let's look at the performance of Nile and its various incarnations. At the very low end is our classic ASP implementation of Nile using a VB6 COM object that does some mid-tier business logic plus also database access. Running out of proc with IIS5 on Win2K using SQL Server through ADO.NET. So that's what we have. So we have some pretty good numbers, and this is the technology that many sites are deployed on today. So you take that and you run it in proc with IIS5, you get pretty good performance. You actually improve your performance quite a bit, but the reliability of your site could go down pretty drastically. And then we'll compare that to ASP.NET running out of proc with IIS, running on top of Win2K, IIS5, using the SQL Server, same SQL Server database, using our highly tuned ADO.NET SQL Data Reader class. We'll talk a little bit about SQL Data Reader. It's actually one of the most performant ways to access database today. So take the same thing and run it out of proc, run it in proc. That's what you get on IIS5. It's pretty darn good performance. The scalability across 2 proc to 4 proc to 8 proc is pretty darn good. It's really, really good numbers, and it compares very well to the best applications that you can write in unmanaged code today. So we've taken the same thing, and because we get this question pretty often from people saying, okay, how does it look compared to if I write a nice API DLL in C++ and deploy it in proc, how does it compare? It actually compares pretty well. It really, really does a good job, and we've been pretty proud of that. It's a pretty good story there. So let's look at one of the things that Paul didn't talk about yesterday is how does this compare to competitive technologies out there? For example, to WebSphere and others. I was actually not allowed to put names on my slides in this talk, but I'm going to name them. What we use here is WebSphere 4.0, the latest and greatest incarnation, running on Linux 7.1, using the Oracle database as a backend. So that's what we have, and it uses Oracle's JDBC driver, the thin Oracle JDBC driver, to talk to Oracle, and that's the performance we see, and it's pretty darn good compared to our competitors, compared to unmanaged code. The performance of this entire platform on server side is really, really good. So let's look at the same numbers. So these are the same numbers from the earlier slide for ASP.NET in proc and ATL server in proc. And let's compare that running on Win2K to our new Windows.NET server, IIS6, with its kernel mode listener to see what type of performance improvement we get. It's actually pretty darn good. This is using the HTTP sys kernel mode listener and really it has a fewer number of transitions as well. So we see a pretty good performance in this world. Plus also, you have the benefits of both worlds. You have this process isolation in IS6 that you can take advantage of. So really, what language do you write in, and whether you target managed or unmanaged apps, is not really a big consideration when it comes to server-side apps. You can write quick managed apps and get pretty good performance out of it. We'll talk about some of the tips we use in improving the performance of these apps in the rest of the slide deck. So the natural question, I think some of the people actually up here were asking, why do we have this win? Why is the performance so good? And yesterday, we talked about the Pet Store app as well. I'm happy to take questions towards the end, and there's actually folks from Vertigo Software here as well. So if you have questions on the Java Pet Store app and why do we see that kind of a win, we're happy to answer that towards the end. But let's talk about generally about why do we see this win. We see this because in this world, everything is early bound. And not only is it early bound code, unlike ASP world, it is compiled. There's absolutely nothing in CLR that is interpreted. Not only is it compiled, our JIT compiler does a very good job optimizing code. For example, it does method inlining, and it does many of the end registration of locals and many of the same optimizations that you get from traditional backend compilers. We'll talk a bit more about the type of optimization later on in this slide deck. And we have some really cool features such as output caching. By the way, we've done some benchmarks on the same Nile using PHP as well, and we actually look pretty darn good. For example, there's no such thing as output caching in PHP today. And we're looking at a pretty broad set of competitive technologies. And features like output caching, which are pretty pragmatic, give some pretty big win. In the earlier slide that I've shown you, all three on the right-hand side actually use the same amount. Both the ASP.NET, ADL server, and the WebSphere one use the same amount of output caching. And the actual output cache searches on the web page. So that is another big reason why we get that win. And finally, we really have a very scalable and highly performant foundation for this platform. For example, the CLR is a great example of that. Our GC really is one of the best in the industry today. We have benchmarks internally that compare it to other GCs and elsewhere, and we have really tuned it very, very well, and we have some novel innovations in that area that make it the best of breed of any virtual machine out there today. We'll talk about some of those aspects later on. And I already talked about the JIT. And we have built-in thread pool. That's actually pretty novel as well. There are not too many VMs that I know of that have a built-in thread pool that scale really well. And you need the built-in thread pool as opposed to using the OS thread pool, because if the GC decides to pause the threads and collect, you need the thread pool to be aware of the GC. You need the thread pool and GC to be aware of each other so that they don't get confused. So that's one aspect of it at the very bottom, bottom of the foundation. The second reason we have that is because our ASP.NET pipeline is super efficient. And it's really, really well tuned. And similarly, ADO.NET, for example, uses the TDS protocol. It's a very low-level protocol to talk to the SQL Server database. So system data SQL client is really a very well optimized class for that. It is actually the fastest way to access SQL Server today. It's actually the fastest way to SQL data readers, the fastest way to access SQL Server. We measure that internally. It's about 1.5 times faster than any unmanaged implementation we have. So all of this combined together as an entire stack give you the performance there. So that's pretty much it. That's so much for numbers. Let's talk about, I'm going to talk about some best practices you can use in your applications that give you these kinds of wins. So one of the key points is you should really minimize throwing exceptions in your code. This seems almost obvious, but it's a very good practice to have. In managed code, you actually don't pay for having EH, but you do pay when you throw the exception. And throwing exceptions degrade performance quite a bit because I got to do crawl the stack. And we have performance counters today that tell you exactly how many your app is throwing. So watch the perf counters, look at what your app is doing, understand what it's doing, and really make sure that you minimize the number of exceptions that are thrown. And the next tip actually I'm going to talk about sounds almost silly, but if you have any unhandled exceptions, especially in the context of a web server that you have, and you're measuring the performance of that app and you're stress testing it for the first time, we're running into this internally ourselves. These are some of the things that we learned. What happens is that your perf goes down because your client that you're measuring it with may not know that there are exceptions being thrown on the server side. So it's something to watch out for and make sure that you don't have that. And if you have VB6 on our go-to syntax, port it to try-catch. It is faster. So the next step is really to make sure that you have early bound code in this world. This falls into the category of things you can tell us at compile time that we don't have to figure out at runtime, give you much, much better performance. And if you have the type information, let us know. And as to the extent that you can avoid late bound code, including late bound interop, COM interop, it really gives you pretty good performance wins. We've seen internally the same web applications using early versus late bound code. Take the type annotations away in VB, and you see as much as a 50% perf degradation going from fully early bound code to fully late bound code in the web app. And that's really something to be aware of on it. So the other thing that I actually forgot to mention earlier is that languages in this world, all managed languages, for example, VB, JScript, C#, and others, they really have about the same performance. It's not terribly different. It's not like earlier days where if you chose to use VB, you're actually bound to the lowest common denominator, so to speak. It's really, you get really good performance irrespective of the language, and that's part of the reason of having this common language runtime as well. So the use of early binding is really, really important. Make sure of that. You can actually enforce this. The VB compiler has strict options that you can use to enforce this at compile time. And if you're using ASP.NET Page, the ASP.NET supports page directives to allow you to write code that is fully early bound as well. And the next aspect that you should make sure to do is anytime you're making a method call that has a cost associated with it, whether it is a pinvoke call, in other words, you're calling out to an entry point in an unmanaged DLL, you're calling out to a COM interop, you're calling out to a COM object through our COM interop layer, or you're making cross-app domain remoted calls or cross-process or cross-machine remoted calls, you should try to make sure that you make few chunky as opposed to lots of little chatty calls. You may or may not have you may not have a choice in this. For example, if you have an object, if you have a COM component that is existing today, that's already written, that's already out there, you may not have a choice. But in many cases where you do, you should make sure to do that. And the next aspect is with respect to value types. This is really an innovation in CLR that the VMs today do not have. Any virtual machine does not have this. It's pretty simple. I mean, it's a stack allocated value as opposed to heap allocated object. And having stack allocated values for small types really, really gives you a pretty good performance win. And we actually have the Mandelbrot set. I'm actually going to, why don't I go ahead and do that. So what I'm going to show you here is just a demo of Mandelbrot set using value types versus the Java one using classes. So let me look at so what you see here is just all it is a struct. It's Mandelbrot set, as some of you may know, does complex math. and all it does is it defines variables and does addition, subtraction, and other stuff on the complex map. And of course, in the code, they actually run this with the seed as well. So let's run that. So what you see here is that it paints up a Mandelbrot set and prints out a time. I don't know if you can see that or not. It's about 2.2 seconds in our world using value types. So let's do the same thing using a virtual machine. So what you see here, using, of course, there's no such thing, there's no notion of a value type at all. And what you see here is a pretty good performance difference between the two. It's about 0.4 seconds in a 2-second interval. And it really does give us a pretty good win. It actually turned out, somebody asked me the other day, so what happens if we take this class and make it just a regular class instead of a struct in the C# example? So we went ahead and did that. So again, so all I've changed is a struct here to a class, and let's go ahead and do that. So actually turns out even faster. So I just told you, use of value types is great. You should definitely use it. But in this case, the classes turn out to be faster. Why is that? Well, the reason that is the case, where am I? So the reason that is the case is because it turns out that we're copying a lot. So in that value type that you've seen just earlier, it passes around by value, this value type, all over the place. So it turns out the cost of copying actually exceeds any memory reference that you may do. So the judicious use of value types really gives you a pretty good performance win, but you should be aware that if you're passing around value types quite a bit, you're really copying this each and every time, and it may negate your performance. So you should, with any of these tips, really measure the performance of your app as you tune your app and make sure that they apply to you as well. So then they apply the small value types. In that particular case, it's actually turned out to be oops, let me just switch. So it turned out to be a pretty large value type as well. It turned out to be over 16 bytes or so, if I remember that correctly. It really depends on how much you're copying around. So all of our primitive types in the .NET framework, such as ints, decimals, and others, are implemented. Everything above the CLR line in the stack diagram I showed you earlier is managed code. So all of our primitive types are implemented as value types for performance reasons. So the other thing to be aware of is the string in our world is immutable. What that means is that it cannot be changed, and if you change it, it really creates a new object. The string object, if you change it, if you concatenate it, for example, it creates a new string object and has a concatenated value in it. So why do we do that? We do that because it actually gives us pretty good performance optimizations internal to CLR. For example, we can intern the string in CLR so that we only have, if you have two hello worlds in your application, you can only have one reference to that, one actual copy of that at any given time. So strings are immutable. It's really important to keep in mind that, that if you're doing a lot of string concatenation, make sure you use string builder, because it's a mutable object and it has a buffer that you can specify when you create the object, and you can throw stuff in that buffer as well. All web apps are, I mean, my view of the world is that they just are big string concats, right? I mean, there are many times in web apps where you stitch these strings together, so be sure to use that. So again, what I have here is a quick demo that shows you, it's just something quick that I've written on use of string versus string builder and just timing that as well. So this class has two methods, one using strings, two static methods, one using this string to actually concatenate versus use the string builder. And let me go down. use the string builder to append as well. So what I'm going to do is I'm actually going to go ahead and run this. Actually, there's a environment.tickCount property that gives you the tick count, and I'm going to go ahead and run that and see what we get. So what you get is actually the string concatenation. I'm looping over that about 10,000 times. And string builder is almost like unmeasurable in a way. It's actually so low, it's actually less than a millisecond. I have a pretty fast computer too, even though I'm looping about 10,000 times. So it's something to keep in mind. So you can actually step through this in a debugger and look at each iteration the fact that the string object is being changed as well. So I'm not going to take your time doing that, but I just want to note that it's a really important thing to remember. So the next aspect is about the use of for each. For each is a really great construct to iterate over collections. It is totally cool, but the problem is that it does have inherent penalty associated with it, because it has to get the enumerator and get the next value each and every time. So it actually makes more calls when you actually have the top pattern as opposed to iterating over a collection yourself. So I have some snippets of code here, and then the thing to keep in mind is that these types of tips make a good amount of difference in your app only if you tune your hotspots, as opposed to I want people to just go ahead and code as it is, and then look at your hotspots, and then apply these techniques, as opposed to going ahead and doing that each and every place, because I think these differences only are magnified in the hotspots there. So let's quickly look at what is happening in that case. So what I have here, I'm just going to type it because it's actually small enough. So what I have here, I don't know if everybody can see it or not. So what I have here is a class that just iterates over a string, just getting the length of the string and iterates over using each character of the string and prints out the result. I'm comparing that to using for each. And I'm actually not going to show the timings here. Instead, I'm going to ILDASM the resulting assemblies. And I'll actually compile them debug so you can see a little bit more information in there. So I'm going to run ILDASM on, let's look at for each one first. So what you see is the standard stuff in ILDASM. How many of you have used ILDASM before? Okay, a lot of people here. Okay, so great. So let's look at the code. So what you see here in the code is the fact that first it makes a call to, we have all the standard housekeeping here, load the strings onto the stack, and it first makes a call to get the enumerator, and then it iterates over it each time, having to call move next each and every time, and getting the value of that. So let's compare that to what you see if you iterate over that directly. So what you see here is actually far fewer calls each and every time. So you don't see that extra call to move next each and every time inside the loop, and the initial call to get the enumerator as well. So this is something to keep in mind. Again, we've seen in that case, we've seen a factor of 5x difference in performance between the two cases. And if you're just iterating over a small enough collection, it may not make a difference. But if you're iterating over a large collection, or if you're in a hotspot that you're trying to improve, it does make a difference. So keep that in mind. The reason I say don't do in V1 is because in the next release, our compilers are going to emit code that's a little bit smarter for some of things like arrays and others as well, so that you actually get the same performance in many of these cases using for each. So one of the things we do in the managed code is we do array bounds checking. But our JIT compiler is actually smart enough in many cases in design patterns like this to hoist out the array bounds checks once and do it once, as opposed to doing it each and every time in the loop. And There's some conditions where it does not apply, but in most cases it does. And these kinds of patterns, try not to get too smart and try to over-optimize your code, but rather just to let the JIT do its job of optimizing code. And with respect to the JIT, for example, if you use virtual methods, a JIT won't know to inline those methods. But if you use field types, it's really a hint to our jitter to let it know that it could inline that method and get much better performance out of it. And if you have really large methods, large method being anything over 1,000 lines of code or something like that, the time it takes to JIT the method, because our granularity is JITting per method, may outweigh actually what you actually run as part of the method. The classic thing that you do in many of these methods is check the arguments and get out of the method pretty soon. And the time it takes to do that is actually a lot less than it may be to JIT the method itself. So try not to have too large methods or have large number of locals. Our JIT can only register 64 locals and temps, unlike the VC backend compiler. So it can only track so many local variables to put them in registers. So be aware of that and try not to write really, really large method bodies with lots of locals. That's the worst thing you can do for managed code, JIT code performance. And the classic example, the classic benchmark you can run to see this is GCC as part of the spec benchmark, where the VC backend compiler does much better job. There's one method, I believe, has like 100 and some locals. It's like really large number of locals. And VC compiler does a better job. Great. I mean, if you write methods like that, VC probably the unmanaged code may be a much better way to run that. So let's look at the next one. So we talked about best practices that apply to any code, any managed code. Let's talk about some best practices that apply to ASP.NET or web applications. So one of the coolest features we have in this world is caching. You can have output caching on pages, and it's really, I mean, if you don't, it falls into the category of if you don't have to do the work, then your app is much faster. So, for example, if your data changes only periodically, overnight, or something like that, make use of output caching, because what it allows you to do is get much, much better performance based on the duration that you set. So you can tune this in various different ways. You can say, I want to output cache everything. I want to give it a duration parameter. Just put @page output cache equals true in your web app and give it some duration. Or you can say, I want to vary the output cache by parameter. Each of the parameters that's passed into ASPX, and on and on. So many times you may not be able to output cache your entire page. So in those cases, you should use fragment caching. In other words, you can output cache really subsets of your page by writing a user control for that subset of the page. It's actually pretty cool because you may have some personalization or customization each and every time in your page, but you can still take advantage of not having to redo the work by using output caching for that subset of the page. Similarly, there's a cache API, System Web Caching class, that you should definitely check out. It allows you to cache an object, throw that in there, and have automatic expiration and things of that nature. And when used properly, it actually gives pretty good results as well. And the recommendation here is to think of this while you're designing your site, while you're designing your web app, so that you know what can be cached versus not. How many of you know output caching, ASP.NET output caching? Good number, okay? I was going to do a demo otherwise really quick, but actually why not go ahead and do that? So let me show you here. So I'm going to show you a really simple example of output caching. And all you need to do is set the output cache directive in your page. And here I specify a duration of 10 seconds to cache this page. And I say, no, I really don't want to vary it by any of the parameters at all. And all I do is make a call to datetime and convert it to a string and return that back. And I want to show you one more thing as well. I don't know if many people know this or not, but output caching applies to web methods as well. And it's pretty cool because you can use the same output cache in making sure that your web methods are not executed each and every time. You can get pretty good performance of it as well. So take advantage of that in designing your app. I'm actually not going to run that on it. So earlier I showed you numbers for Nile, and I mentioned the fact that output cache was on in those cases in a subset of the application. For example, the search page and a few other pages were output cached. And let's look at what you get in that particular case when you don't have the output caching on. Really, this is an example for Nile app. I mean, you can really tweak these numbers depending on how long you cache them. So as you can see, actually, the WebSphere one gets a much better performance than output cache because it really, when you have a slower mid-tier, and if you avoid that code path altogether, clearly you're going to get much better performance. So when they output cache it, they get much better performance percentage-wise performance than we do. So the next aspect that I want to talk about is session state. Session state is a very useful feature in ASP.NET, and it's really cool because in ASP you could not really share session state either. But if you don't need it, and it's on by default, so if you don't need it, if you don't have a shopping cart or if you don't have something else that you're tracking, it's really an overhead. You should turn that off. So there's in-proc session state, out-of-proc session state, and session state that you may store in a database as well. So each and every one, it actually degrades as you go to a database in terms of with respect to performance. So if you're storing session state, especially in a database, you should really think about whether you need session state for that page. Again, this is a feature versus performance trade-off that you can do in your app, and turn that off if you don't need that. And you can do this at multiple levels. You can do this for the entire application in web.config file, or you can do this just for the page, or you can do it for any given control. It's a property and a control that you can set as well. Similarly, there's the notion of view state in ASP.NET. How many of you know what view state is? Good number, okay. So view state is that ability when you go back and forth in a page, it preserves that what you selected. But, for example, if you have a list box and you selected something, the way it knows to reselect that back is making a server round trip and getting that data back. And it's additional payload to your page. You may or may not want that. It's on by default for server-side controls, and it's something you should consider turning off if you are trying to improve the performance of that page. And again, you can do this in multiple levels. For example, you can do this, you can say, I really don't want view state at all for my app. You can set that in web config. Or you can turn it off on a per page, or you can set a property on a control to turn it off per control as well. So you can turn the dial at each and every way. So one of the biggest perf losses that I've seen, actually a lot of people have done this, have made this mistake, is you tend to use an STA component from your ASP.NET app without doing anything else. And what ends up happening is that you tailgame the STA component, and it's okay, great, I'm going to use it from my ASP.NET app. What ends up happening is that you're talking from an MTA world, a multi-threaded world, to an STA component, and COM creates these proxies to go communicate. Basically, marshalling is happening on each and every call, and that's a significant performance loss. Not only that, the best way to do this is really to set the ASP compat flag in your applications so that that thread is marked STA by ASP.NET. It actually uses the STA thread pool to talk to that COM object, and thereby you really are talking from STA to STA, and you really don't have this additional overhead going on. Again, this tip falls into the camp of if you know at design time that information, let us know, so we don't have to at runtime figure out that information and do additional work in the context of your app. And there's one tip here. We've actually noticed this. If you're creating if a comma object in the page constructors, what ends up happening is that they get created on empty a thread anyway, and it does pay that penalty, and that thread is, and that page is then marked pretty much empty A. So try not to do that. We've actually run into this in an internal application that we're measuring as well. And if you can afford to do that, again, I'll emphasize this. If you can afford to move your COM objects to .NET components and port that code, it's best to do that. All the numbers I've shown you earlier are with respect to fully managed code where there are no managed to unmanaged transitions happening, and that gives you the absolute best performance that you can. So in the web apps, what we've seen is a COM object being used in a web app as opposed to the same COM object ported to a .NET component can, there's about 20% difference in performance, can negate the performance by about that, but that your mileage varies based on how chatty your layer is and things of that nature. So this is an approximate thing to keep in mind. So that's pretty much it on web apps. I want to talk some more about client-side apps and WinForms. So we have some great story on web apps, and I've showed you what we have and talked about some of the tips you can use. Let's talk about WinForms apps, and the kinds of things that you worry about in client apps are working set, startup time, and of course the overall what happens when you bring up a second app, what is the additional working set overhead, and things of that nature. So this is one of those areas where we don't have as good a story as we do on the server side, but we have a pretty good story with respect to our competition. So I'm going to show you some numbers. Just hang in there. So you write something like console, right line, hello world, and look at the working set of that app. What does it look like? So look at the startup working set of console, right line, hello world. It's about 2.5 meg. The reason it's 2.5 meg is because it's got to spin up in the stack diagram that I've shown you at the very beginning of the entire framework. It has to spin up the common language runtime. It has to spin up then the JIT subsystem, the security subsystem, and on and on and on. I'm going to score JIT.dll, I'm going to score sec.dll. Plus also it has to spin up part of the base class library, I'm going to score lib.dll, just to run console right line hello world. So there's that one-time overhead with respect to working set that you pay. If you write in C++, something like this, I think it's about 600K or so. So what I'm saying here is that you cannot extrapolate linearly with respect to this and say, okay, so every app's working set must be 4 times larger or whatever. You cannot do that. This is a one-time, as you spin up more and more of the stack, you bring in that working set into your process. So you write an empty form, just bring up in a WinForm, you go more and more up the stack. What does it look like? So what you see is about a 5 meg working set when you do that. And again, when you add, how does it scale if I add about 100 controls to the page? So what you see here is about a 5.5 to 5.6 meg working set. By the way, all of these measurements were done in a fully pre-JITted environment. We'll talk about pre-JIT in a bit as well. So on and on. As you bring in data, you add an additional meg. That's actually not a 1 meg, just 1 meg. It's just additional meg of working set as well. So as you spin up more and more and more of the framework, as you use more classes in there, you do pay that one-time penalty. You should be aware of that as you write client apps, or even server-side apps for that matter. But one of the key things is the fact that many of our pages, about a good 3/4 of those pages, are either shared or shareable. In other words, the second app that you bring up shares many of those pages with the first app. So the delta in working set is not that much at all. And what I've talked to you earlier about is a startup working set. Our steady state working set, in other words, those few pages that you need to run the app in steady state, you minimize it, you maximize it again, is much, much better. It's more in line with unmanaged code. We've actually had some folks internally, the Windows team, experiment with rewriting add remove programs using managed code versus unmanaged code. What does it look like running on top of CLR? And using some best practices, and that's what they've seen, is that there is a delta in the startup working set and startup time between managed and unmanaged code. But in the steady state, it's really falls into a noise category as well. So that's the working set story. And It is something we are continuing to work on in our next release. It's one of our highest priorities, but we compare very favorably to any of the other runtimes and their client-side story as well, whether it's Swing or whatever you may want to compare it to. So what are some of the tips that you can use in improving the performance of WinForms apps? Well, if you have a collection of things that you want to add to a control, there are a couple of different ways you can do it. You can iterate over that collection and call the add method on the control each and every time, or you can just add the collection once using the add range method as well. So that's something you should keep in mind. It does give you a performance win there. And the second bullet is actually a key one. You should really try to minimize the number of assemblies that you load in your app. In other words, number of DLLs that you pull into your app and their transitive closure of dependencies really can increase your working set. You should make sure to take dependencies very carefully. And the other thing that we noticed is that if you use data classes, connection pooling in this world is on by default. What that means is that it brings in a ton of DLLs into your working sets, such as MSDTC and others. But the problem is that you may not need the connection pooling to be on. If you're writing a client app that goes and grabs a bunch of data and comes back, it really is not, you're not trying to scale that app. You're not trying to like push its limits. You may not need connection pooling. So you can turn that off by passing in a parameter in the connection string and save yourself about a meg in working set, because the DTC and other DLLs don't come into your the image of your process. So that's something to keep in mind. Pre-JIT is a technology that we're actually pretty proud of. That's how we improved much of our working set between beta 1 and beta 2. And a pre-JIT image is really just a JITted form of MSIL in a PE file. It saves you two things at startup time. It saves you the JIT time to JIT the methods, those methods that you touch at startup time. And secondly, it saves you the class layout time as well. So what you have is pre-laid out JITted image that you can just read into memory and run. And the way you do this, because we actually do some processor-specific optimizations in our JIT, is you do it actually at install time. You really don't pre-JIT an image and say, okay, I'm now going to deploy this pre-JITted image across machines. That's not the model. What you do is you add a custom action to Darwin or some of this, whatever setup program you use. Actually, somebody can get the lights. Great. So whatever setup program you use, and you add a custom action to pre-JIT that image by using our tool called engine.exe, which is new, starting in beta 2, and you deploy that app. And much of our framework, MSCoreLib, WinForms, Drawing, others, are pre-JITted very much to improve the client-side app performance as well. And the time you decide to use pre-JIT is if you're writing a client app, it doesn't apply on the server side at all for several different reasons. If folks are interested, I actually can get into that towards the end of the talk as to why it doesn't apply. Actually, ASP.NET just ignores it if you pre-JIT your app anyway. But it applies for WinForms client-side apps where most of your dependencies are on the system anyway. And it does give you a pretty good startup time then on the order of like somewhere between 10 to 20%. And your mileage could vary based on that. So it comes to using pre-JIT, and you should definitely, as with any performance tip, make sure you measure that to see if that cost is worth the benefit. I mean, if the complexity is worth the benefit. We have internally this benchmark called complex form. All it is a form with about 100 controls, throwing buttons, checkboxes, and others as well. It's a WinForms form. And what we see here is the improvements that we had from beta 1 of our product to beta 2 of our product. We've worked on performance and improved the working set and startup time tremendously. But with that said, between beta 2 and RTM, we don't have the similar wins. We haven't done as much work. So what you get for beta 2 is pretty much what you get for RTM. It's pretty much the performance that you get for RTM. In other words, RC bits that you guys have won't be that much better than what you see here. And that's pretty much our V1 story there. So that's pretty much the tips and tricks section, and let me drill into CLR a bit. I mentioned GC. Our GC is known to be the best in the industry today. It's a marked compact garbage collector. Today on server-side apps, when I go to NT-perf team meetings, it's Windows NT-perf team meetings, the biggest issue that we have for long-running server-side apps is really fragmentation. Our GC really attacks that and really does a good job at that because it's a compacting heap, and it really helps on server-side quite a bit. And it does support some interesting aspects. So now in C++, you can have things like interior pointers, and you can pin an object and say, don't move this object, because you can just tell GC not to move that object because you may have passed it out on managed code, anything like that. And we have two different architectures of the GC. We have the server-side GC, that is the default if you write an ASP.NET app. So ASP.NET hosts the common language runtime specifying a server-side GC, which is a highly scalable multi-heap GC as well. And it doesn't take locks in allocations, so it actually scales really, really well. And our client-side GC is designed with a different set of characteristics in mind. For example, the things that you care about on the client side is for the user not to notice any pause time at all. That's really the thing that you care about the most. So on the client side, the GC runs concurrently with the app. It's a separate thread. If you notice on the WinForms app or any others, it's a separate thread that runs concurrently collecting from your app. So it does not pause the app except for the what we call a Gen 2 collection. And in between these two extremes, which are, by the way, servers, the MS-core srv.dll that you see, and the client one is the MS-core wks.dll. So these two GCs are implemented in those two DLLs. That's pretty much the only difference between those two DLLs. The rest of the EE is about the same on it. Just the GC is really different there. So in between these two extremes is a batch processing app. So in these two cases, whether it's the server or the client, the default that you get when you run on top of the .NET framework is the correct default for the client and the server. In between the two is a batch processing app that you may write. For example, you're parsing a large XML file, megs and megs worth of data, and what you care about is the end-to-end throughput, and you may not care about anything else. So in that case, you should consider turning the concurrency off on the GC. And the way you do that is you bring up the runtime configuration tool in the administrative tool section, and you can switch and say, I really want the GC to run the same thread as the app, and I don't want it to run concurrently with the app. And that's, if you're writing a batch-style app, that's something to keep in mind. Our GC is mostly self-tuning in many of these cases as well. I mentioned the multiple generation aspect already. Our GC maintains the Gen 0, Gen 1, Gen 2 based on the lifetime of the object. All allocations are done on the Gen 0 heap. And you may not, those objects may not live for a very long time, in which case, GC collects those objects, and anything that lives beyond the Gen 0 collection gets promoted to Gen 1. And by segmenting the memory that way, it actually gets some really good performance wins as well. A GC is very cache conscious. Part of Gen 0, part of the reason for segmentation this way is that we try to fit Gen 0 into the L2 cache so that most of your allocations there are happening right. Just you're not even touching main memory. And I mentioned the low fragmentation aspect already. It really does a good job of compacting, and the overhead of the GC itself is not very much. It's actually very, very low. Another key design point of our garbage collector is that it keeps the locality of reference intact. In other words, you allocate two different objects, A and B, together. Even when compacting and moving the heap around, it keeps those locality intact because it's a well-known, really corollary. Things that you allocate together are those that you use together. So it really keeps the locality intact and does a really good job with it as well. It gives a good performance win. And we have a separate large object heap for really large objects. It is, I believe it's on the order of 80K or above. that the GC just maintains separately, independent of Gen 0, Gen 1, and Gen 2 subsections of the GC heap. So what does the performance of the GC heap look like? Fundamentally, it's really limited by PC bus speed. I'm still trying to benchmark this on various different architectures, including trying to get the AMD machines with the front side bus to verify this claim. And so far, it really is. Our GC is not limited by anything else. It's how much you can allocate and the bandwidth on your PC. And the pause times are very minimal on as low end as we get. By the way, the minimum configuration that we recommend is like P133, and these are published in the documentation as well. So it depends on whether you're running server-side app or client-side app and all the details of it. So the pause times are actually not that much. I mean, for Gen 0 collection, it's less than a millisecond. And for Gen 1 collection, it's on the order of, it's about an order of magnitude more. It's about 10 milliseconds. And full GC, where you're collecting and compacting the entire heap, varies with the full working set. And it is very infrequent on it. You can look at and measure many of these using our performance counters as well. So let me show you a quick tool, and I'm just running a little bit over, so I'm going to. So this is the tool that I've noted that you have both the binary and the source for on the resource kit that I pointed out at the beginning of the talk. So what this tool allows you to do is look at your GC heap. And the way it does that is by talking to the profiling APIs in the common language runtime. I'll briefly talk about the profiling APIs in a bit. So this is a managed app. In other words, it's a WinForms app that is talking to a COM object that talks to a profiling API to get at the object creation callbacks and show you what is on the GC heap. So I'm going to run it on itself and look at. So what I'm going to do is I'm going to bring it up. And have some really cool features, like you can say, I want to see the heap right now. So what it does, it shows you the heap. Let me increase the font here. Let me make it 16. And so what you see here is, you see the fact, okay, scrolling issues on it. All right. So what you see here at the root is you have about 124K of allocations in the allocation profiler on the GC heap. And that 124K breaks down into these sub-allocations on that. So you can say about 52% of that came from that subgraph, and another 27% of that came from that subgraph. And you can do things like, you can Control A, Control C, and then you bring up Notepad, and you can paste it, and you can show you the stack and where things are coming from, and the breakdown of coming from, and the breakdown of coming from, and the very good and very deep way to introspect your GC heap and see exactly what you're allocating and from where you're allocating this information, this memory there. So it also has, so I'm just going to quit out of here. So also has a couple of interesting aspects as well. So I'm going to run this again. Actually, no. So, but this time around, I'm actually going to look at the call graph as well. So what I'm seeing here right now is that looking at the allocations. So looking at the allocations in the context of the various methods that I have. So in this application, which is the WinForms app, the Form 1 main formed about 85% of my allocations, and 287K that I've allocated from there. And on and on and on, it breaks into the subtree of that and shows you a graph of all of your applications, and you can set some interesting properties of it. So in other words, you can also have you can compare GC heaps. You can take a snapshot of the heap now, you can run it later, and you can take a snapshot of the heap later, look at the delta between the two and say, what is growing in my GC heap? And one of the biggest problems that we have in the managed world is one of really memory retention. It's too easy to allocate and hold on to objects for far too long and not allow the memory to grow. What this allows you to do is improve the performance of your applications by reducing that bloat. And you can get different levels of detail for everything. I want to know about every allocation to only want to know about the big allocations, to the scale of it, to you can do all kinds of things. You can prune the subgraphs and filter it for any specific thing that you're looking for. For example, if you're looking for all the system classes, or you're looking for all the system classes that allocate and things of that nature, so you can filter for that. So I'm actually not going to demo this any further because you actually have a pointer to this in your PDC resource kit. It's not just the binary that you have actually let me just go back, I don't want to still show yet. It's not just the binary that you have the pointer for, it is both the managed code source and the unmanaged code source that form this allocation profiler. So it shows you a very good sample of how you can write some interesting applications using our profiling API. So let's talk about transitions between managed and unmanaged code. Runtime makes it really simple to call the OS, and that's a design point of the runtime as opposed to many other VMs out there. And these transitions happen when you call managed unmanaged and managed managed. And at each of these transitions, we need to do some work. We need to do data type marshalling because the type systems on both of these worlds may be different. The runtime type system will be different than any OS that it may be running on top of. There's 9x, do ANSI to Unicode, any other conversions there, or running on NT. So looking at, you need to do data type marshalling, and you need to do data type, fix up the calling convention, and we need to do some housekeeping when we make this mode switch. So what does all of that mean? That means that there's a cost associated with making a managed unmanaged call. And these were measured close to beta 2. And take these as approximate guidelines, please, not as exact numbers for number of instructions. So what you see here is that to make a p-invoke call out to an entry point in VLL could be as low as 8 instructions if it's like a void call. But the problem is that you never do that, right? I mean, you pass in something and you bring in the marshalling layer. So when you do that, it's typically around 30, 40 instructions at the minimum. That's the baseline cost when you make a p-invoke call. And on the common prop, it's about 60 some instructions when you make a call. Again, that's a baseline call. All these numbers are clearly taken with the security turned off, just to isolate the noise and make sure that we have the transition costs as opposed to security costs associated with it as well. Security would be a lot more. And then there's the incremental cost or variable cost associated with the number and the type of parameters you're marshalling from managed to unmanaged code. So the primitive types, you're passing an int. Really, I mean, int is known in both worlds. There's really, all you need to do is copy that over. So there's no cost involved there. But in COM world especially, we have this type system, great type system of beasters and variants and others, where you need to unpack the variant, know the type, and really do some work there. What that implies is that it really depends on the variants and beasters, and it could be on the order of hundreds of instructions based on what you're marshalling across the boundary, especially if you have to do data transformation from ANSI to Unicode to ANSI and on. So keep that in mind in making managed unmanaged calls, and try to minimize, try to make a call that is at least that is worthwhile. In other words, if you have a base cost plus marshalling of let's say a couple of hundred instructions, it doesn't make sense to make a call out on managed code. It may make sense, you may not care about that, but in performance critical code, it may not make sense to call out to code that is 20 instructions. Clearly your overhead is 10 times in that case. So our JIT does a ton of optimizations, and these are all pretty standard optimizations as well. For example, it inlines methods. And there's limitations on how large a method it could be, and others, but it does inline methods. It does all the standard stuff such as constant folding, copy propagation. It does CSE, and dead code elimination, and registration of locals, and on and on. It does all the standard stuff that many backend compilers do today. It does loop unrolling as well. I actually don't have that on here. But these optimizations are much more restricted and limited. I gave you a couple of examples. And registration of locals. Unlike a VC backend compiler, we can only track so many locals and temps. And same thing with method inlining, and same thing with each and every one. So we make some pragmatic decisions because JIT compile time is part of the runtime. We make some decisions based on that and say, look, it's better off not optimizing this any further, because the time it takes to optimize may outweigh the benefits that you get from optimizing that code. And in our V1, our pre-JIT really calls into a regular jitter, so the optimizations that you get both ways are the same. But in our next release, we actually intend to improve on that and try to use our backend compilers to really tie that into the pre-JIT so that you can get all the optimizations that you get out of the backend compiler in the managed world. And that's pretty powerful, and that's something we're looking into much further. So by the way, there's a talk on Friday by Jim Hogg on how does Hello World really work, where he's going to walk through each bullet item in here. It's Friday at 9:30 a.m. and show you a demo of the resulting IL, x86, what happens, and you need a full hour just to go through that on it. And plus more. So do go to that if you care about knowing what optimizations are happening underneath the covers. So I talked about CLR. I'm going to actually go through the tools really quickly because you have all these pointers on the CD that you have. So performance counters, they come free in this world. How many of you have played with the perf counters already in the CLR? A lot of you? Okay. So I'm going to skip through that slide. So the perf counters that matter, at least that we learned when it comes to managed apps, are mostly in the memory, the second one. It's very important to know what is happening with your memory, and the percent of time spent in the GC, the number of bytes per second, and various heap sizes that you're allocating is very, very critical to know. Know those, and again, you look at the interop counters, look at the number of transitions you're making, on and on. Similarly, in threads and locks, you can look at the number of contentions and JIT compilation. What are you JITting? How much time are you spending in the JIT? And the number of exceptions you're throwing, on and on and on. And all of these are available programmatically as well through our system diagnostics performance counter class. It's actually very simple in managed world to create a performance counter compared to unmanaged world. It's just a few lines of code. And actually the source for one of the tools I'm going to show you is available on the CD. Again, the source is available on the CD, and that uses many of these classes as well. ASP.NET has a ton of counters. For example, you can look at the top level, the number of requests that you have, the number of requests that you have in the queue. Is your queue length growing? That's a key metric to measure if you have a web app and you're trying to see what is happening with respect to the web app. So let me do a quick demo. So what I'm showing you is I'll have the allocation profile up and running. What I'm going to do is run this tool called perfstats that it's no magic to it. It just we actually wanted to write a tool internal to the CLR team that we can give out to people whenever they say, well, I have a perf issue with my managed app. That gives us a pretty good top-level sense of what is happening because we get a lot of those questions internally in Microsoft. So what it does is it looks at the performance counters for about 10 seconds on that app and gives you the max, min, mean in that time frame. For example, it gives you all of the .NET perf counters, and it breaks down the working set. I'm going to let it scroll by, and I'm going to show you in a bit. It breaks down the working set as well. So I have it ran this earlier, and it gives you a ton of information about your system. And for example, I'm going to skip to the managed counters because that's the most interesting part to me, at least the context of this talk. So the number of performance counters in the .NET CLR JIT category, the number of methods that you've JITted, and on and on and on. The number of classes that you have loaded, that actually makes a big working set impact, so you should try to minimize the number of classes loaded. The number of GC collections that are happening, and on and on. And then it does a working set breakdown of, I think you can see the whole thing, yeah. Working set breakdown of where is your working set coming from. In this particular case, it's really a simple WinForms app that uses our system assembly, so most of the working set is coming from the system. But it gives you a very good breakdown of that as well. So I strongly recommend that you take a look at that. You need to have VA dump on the path as well, because in the end, all it's doing is running VA dump for this subsection of it. And it's a managed sample, perfstats.cs. So take a look at it and let me know if you have any questions or comments or improvements that we should make to that. going forward. I'll briefly talk about profiling API, and then I'm going to wrap up and take some questions. Profiling API, the profiling API in the common language runtime is what allows you to look at many of the events that are happening in the runtime. For example, in the allocation profiler that I've showed you earlier, that shows you the objects that you have in your GC heap, it is really using the profiling API in the background and getting the callbacks for that by subscribing to an API called iCore Profiler Callback. So you get a callback each and every time an object is created, and then you can use iCore Profiler Info to get at much more detailed information at that. So the reason I'm mentioning this is because it's really simple to write a custom health monitor or custom tool that allows you to look at what is happening in your managed app.